Right now, there's a device the size of a coaster, chilled to a temperature colder than the empty space between the stars, that finished a calculation in under 5 minutes. A calculation the most powerful supercomputer humanity has ever built would need 10 septillion years to complete. 10 septillion. That's a 1 with 25 zeros trailing behind it, a stretch of time so long the universe itself has only existed for a rounding error's worth of it. And here's the part that actually pulls people down a rabbit hole they can't climb out of. The scientist who runs the team that built this thing didn't just brag about speed. He publicly floated an explanation that most researchers at a company that size would never dare put their name to. An explanation that reaches outside our universe entirely. There's one number buried in this story that breaks ordinary intuition so hard it makes people question where computation even happens. Hold on to that. We'll get to it. Let's start with what this actually is, because the headline version and the real version are two different animals. In December of 2024, Google's quantum computing division introduced a new processor. They named it Willow. And within days, one comparison had spread across the entire internet. 5 minutes of work on Willow versus 10 septillion years on a classical supercomputer. That comparison is accurate, it's published, and it's genuinely staggering. But if all you take from this story is the quantum chip is fast, you've missed almost everything interesting about it. Speed isn't the wild part, scale is. This wasn't Google's first swing at this either. Back in 2019, an earlier Google chip called Sycamore made a similar claim, that it had done in minutes what would take classical machines an impractical amount of time. But that earlier claim came with an asterisk. Skeptics argued, reasonably, that ordinary computers running cleverer software might eventually catch up and shrink the gap. And in the years that followed, that's partly what happened. Researchers did develop smarter classical methods that clawed back a chunk of Sycamore's supposed lead. So the doubt lingered, and honestly, it should have. That's how science is supposed to work. Now here's why Willow changed the temperature of the conversation. It arrived several hardware generations later, and its gap over classical machines wasn't a matter of a few percentage points that a clever programmer might someday erase. It was a difference of raw category, an entirely different order of magnitude. When the gap is that enormous, the classical computers will catch up argument stops sounding like caution and starts sounding like wishful thinking. To put it plainly, this no longer looks like two runners on the same track, one slightly ahead of the other. It looks like two completely different kinds of motion. One is walking, the other isn't even using the ground. And that distinction between a faster machine and a fundamentally different machine is the thread that runs through this entire story. Because to understand why Willow's numbers get so strange, you first have to understand what makes a quantum computer a genuinely different species of machine, rather than just a souped-up version of the laptop on your desk. So who's behind this? Google's quantum research effort is led by a physicist named Hartmut Neven, and his lab has spent years chasing exactly this kind of milestone. Keep his name in mind, because he's the person who's about to say something that sent physicists and journalists into a debate that still hasn't cooled down. Here's the number I told you to hold on to. It's not the 10 septillion years. That one's shocking, sure, but it's still just a measure of time, and humans are at least a little bit used to giant time spans. The number that genuinely breaks intuition is this one. Willow operates with 105 quantum bits. And by the time you link that many quantum bits together in the right way, the number of distinct states the system can represent at once becomes larger than the total number of atoms in the entire observable universe. Read that again, slowly. A machine small enough to sit on a lab bench is juggling more possible configurations than there are atoms in everything we can see, every star, every planet, every grain of dust across the whole visible cosmos. So how is that even possible? A classical computer, no matter how blazingly fast, does its work one path at a time. It takes a question, marches through the steps in sequence, and arrives at an answer, the same way you'd grind through a long division problem line by line, no matter how quickly your pencil moves. Faster hardware just means a faster pencil. The fundamental method never changes. One step, then the next, then the next. A quantum computer refuses to play that game. Instead of bits that must be either a 0 or a 1, it uses quantum bits, qubits, and a single qubit can hold a blend of both 0 and 1 simultaneously. That property is called superposition. Just by itself, that lets a quantum system carry many possibilities in parallel rather than checking them one at a time. But superposition alone isn't where the real fireworks come from. The explosive part shows up when qubits become entangled, linked together so tightly that the state of one is bound up with the state of another, regardless of how the system is laid out. Once qubits entangle, the number of states the whole system can represent doesn't merely add up or double. It multiplies out of control, exponentially. 10 qubits give you over 1,000 states at once. 20 give you over 1,000,000. 50 give you more than a quadrillion. And by the time you reach roughly 100, right where Willow lives, you've blown past the atom count of the observable universe. That's not a metaphor or a rounding up for drama. It's just what the math of exponential growth does when you keep doubling, and it forces a genuinely uncomfortable question that most coverage skips right over. Here's the question, and it's the kind that keeps physicists up at night. When your laptop does its work, you can point to exactly where that work happens. It happens in transistors, physical switches flipping on and off inside a chip you could literally hold in your palm. Every scrap of that computation lives somewhere you could touch. There's no mystery about the location. Now apply that same logic to Willow. If this chip is somehow working with more possible states than there are atoms in the observable universe to physically represent them, then where exactly is all that work taking place? It can't just be happening inside the chip. The chip is made of a finite number of atoms, a countable amount of matter, and that amount falls catastrophically short of what the calculation seems to require. You'd need more storage than the universe contains, packed into something the size of a dessert plate. That doesn't add up in any ordinary sense. Let me try an analogy the source of this story didn't use. Imagine you hand someone a single sheet of paper and ask them to write out every possible chess game in full. Not the famous ones, every single legal sequence of moves that could ever be played. There are vastly more possible chess games than atoms in the universe, so obviously the paper can't hold them. It's physically impossible. Yet suppose that person somehow handed you back the single best move in any position you named, instantly, every time, as if they'd actually consulted all those games. You'd be forced to ask, where did that consultation happen? Not on the paper. The paper's too small. So where? That's the corner Willow backs you into. The machine appears to behave as though it consulted a space of possibilities far too large to fit inside the machine itself. And that's precisely the point where the conversation stops being about engineering and starts brushing up against philosophy, against the deepest unsettled questions about what reality is actually made of. It's worth being honest here. This is not a question that engineers trained purely in circuit design are equipped to answer on their own. It's a physics question, maybe even a metaphysics question. And it's the exact doorway through which Hartmut Neven walked when he made the claim that turned this into international news. But before we get to that claim, we need to understand how the machine actually pulls off its trick E, because the mechanism is where the strangeness becomes concrete instead of hand-wavy. So how does a quantum computer actually arrive at a right answer, rather than just drowning in a septillion wrong ones? This is where a lot of explanations wave their hands and move on. Let's not do that. The engine underneath a quantum computer is a phenomenon called interference. And here's the thing. You don't have to believe anything exotic about parallel universes to accept that interference is real. Even under the most cautious, conservative reading of quantum mechanics, interference is simply how these machines work. Picture the qubits as waves rather than switches. Waves can do something switches can't. They can overlap. When two waves line up crest to crest, they reinforce each other and grow stronger. When a crest meets a trough, they cancel each other out and flatten to nothing. Quantum states inside the processor behave in exactly this way as a calculation runs. The states that lead toward the correct answer reinforce one another, building up like waves stacking in phase, and the states that lead toward wrong answers interfere destructively, canceling each other out until they vanish into the background. There is no equivalent to this in a classical computer, none. A regular chip has no way to let its wrong answers erase themselves. Interference, in a very literal sense, is how a quantum machine lands on the truth instead of just producing noise. And this reframes what a quantum programmer actually does. Writing a good quantum algorithm isn't about brute forcing every possibility. It's about choreographing the interference, designing the calculation so that all the paths leading to wrong answers cancel out as completely as possible, while the path to the right answer gets amplified over and over across the run. It's less like searching a haystack and more like tuning an orchestra so that only one clear note survives while all the discord silences itself. Now, here's where the interpretations split. Under standard quantum mechanics, interference is just interference, a property of quantum systems, strange but self-contained, requiring nothing outside our universe. But under a different framework, the one Neven leaned into, that same interference gets read as something far wilder. A faint, limited overlap between separate branches of reality. Not communication. Nobody sending messages across universes. Nothing like a phone call to a parallel Earth. Just a whisper-thin form of shared computation, bleeding across branches enough to nudge the final result. Willow does not prove that reading is correct. Let's be crystal clear about that. It doesn't open a portal, and no researcher involved claims it sends or receives anything from anywhere else, or that a person could ever step through into another branch. But what Willow does do is drag a decades-old, purely theoretical debate out of the seminar room and plant it right in front of a physical device you could hold. The abstract argument suddenly has hardware attached to it, and that's what makes the next part land so hard. So let's finally get to what Hartmut-Neven actually said, because this is the moment the story went supernova. In the blog post announcing Willow, Neven didn't stick to careful engineering language. He argued that the chip's performance was so far beyond what a single universe seemed capable of producing that the most natural explanation was that the computation had, in effect, drawn on resources from parallel universes. He said the result lent real credibility to the idea that we live inside a much larger multiverse, and he explicitly tied that framing to the earlier theoretical work of physicist David Deutsch. Now, where does an idea like that even come from? It didn't originate with Google. It traces back decades. In the 1950s, a physicist named Hugh Everett proposed what's now called the many worlds interpretation of quantum mechanics. The core notion is genuinely dizzying. Every time a quantum event could go more than one way, it doesn't just pick one outcome, it produces all of them, each branching off into its own separate strand of reality. David Deutsch, one of the founding thinkers of quantum computing, later expanded on this and argued something provocative, that when a quantum computer runs, the sheer scale of what it accomplishes only really makes sense if the work is being spread across those many branches, then somehow funneled back into the single answer that appears on your screen. Most people first bump into the multiverse through movies and comic books, where it's a playground for alternate versions of superheroes, so it's easy to dismiss as pure fiction. But here's what surprises people. A meaningful number of serious credentialed physicists, including some who've devoted their careers to the foundations of quantum computing, treat many worlds not as a fun story, but as a legitimate candidate for what's physically true. And here's the crucial wrinkle. Many worlds is one of several competing interpretations of quantum mechanics, and they all make the exact same experimental predictions. Every one of them predicts identical results in the lab. They only disagree about what's happening beneath those results. That's a big part of why this debate has never been settled by evidence, because no experiment yet devised can tell the interpretations apart. They're indistinguishable at the level of what you can measure. So when Neven put his name on the multiverse framing publicly, he was making a genuinely bold move for the head of a major corporation's research division. He wasn't stating settled science. He was staking out a position in a fight that physicists have been having for 70 years, and doing it with a piece of working hardware as his evidence. Predictably, that did not go unchallenged, not even close. Because here's where a responsible look at this story has to slow down and push back. And honestly, the pushback is what makes the whole thing more interesting, not less. Plenty of physicists and science writers objected almost immediately, and their criticisms are worth taking seriously. The first and sharpest objection targets the specific test Willow aced. It's called random circuit sampling, and critics point out something important. This benchmark was essentially designed to be brutally hard for classical computers and naturally easy for quantum ones. It's a task engineered to show off quantum advantage, not a broadly useful, real-world calculation that produces something practically valuable. Think of it this way. If you invent a contest, write the rules yourself, and then win it decisively, that's impressive. But it's fair for people to ask how much the victory really proves outside the arena you built. Because Google both designed and controls this particular benchmark, a number of scientists have argued it's simply not strong enough evidence to support a claim as monumental as the existence of parallel universes. That's an extraordinary claim, and extraordinary claims demand more than a favorable test result. The second objection is even more grounded. Critics note that everything Willow did can be explained using perfectly standard quantum mechanics, interference, superposition, entanglement, without invoking a single extra universe. The multiverse framing isn't required to account for the result. It's one interpretation layered on top of data that other interpretations explain just as well. And there's a third point worth keeping in mind, though it's about incentives rather than physics. Google operates in a fiercely competitive technology landscape, and a company like that has an obvious reason to frame its achievements in the most jaw-dropping way possible. That doesn't make the underlying science wrong. The science is solid, but it's a reason to be a little cautious about how far to run with the most dramatic interpretation of it. So where does that leave us? With an honest picture, this is a genuinely contested question inside physics, not a settled discovery. What almost everyone in the field agrees on is that the raw computational result is real, deeply impressive, and independently verified through peer review, published in the journal Nature. What remains fiercely debated is what that result actually tells us about the deep structure of reality. and reasonable, well-credentialed physicists come down on opposite sides. That's not a weakness in the story. That's what real science in motion looks like, before the textbooks have decided who was right. And now here's the twist, most of the viral coverage completely buried. Set the multiverse aside for a moment, because arguably the most important thing inside the Willow announcement had absolutely nothing to do with parallel realities, and it may end up mattering enormously more in practice. It's about errors. Quantum computers are famously maddeningly fragile. A tiny vibration, a trace of stray heat, a faint stray electromagnetic signal drifting past, any of these can nudge a qubit off course and corrupt an entire calculation. Physicists call this problem decoherence, and for roughly 30 years, it has been the single biggest wall standing between quantum computers as dazzling lab curiosities and quantum computers as machines anyone could actually depend on. Now here's the cruel catch that made this problem feel almost unbeatable. Normally adding more qubits makes things worse, not better, because every additional qubit is one more thing that can go wrong. It's like trying to build an ever taller tower out of wet sand. Every layer you add makes the whole structure more likely to collapse under its own instability. For decades, that was the trap. More power meant more fragility. Willow demonstrated the exact opposite behavior, and this is the genuinely huge part. As Google's team scaled the chip up, bundling physical qubits together into protected units called logical qubits, the error rate went down instead of up. Specifically, each time they enlarged the encoding, moving from a 3x3 grid up to 5x5 and then 7x7, the error rate roughly halved. That's not just holding steady. That's exponential improvement in the right direction, which is exactly what everyone had spent 30 years hoping to see and never quite seeing on real hardware. In the field, this achievement has a name: crossing below the error correction threshold. It's a milestone quantum researchers had been chasing since the 1990s, a line in the sand that separates theoretical promise from practical possibility. Team members have described the moment the data came in as something close to a collective exhale across the whole quantum community, because it finally showed, on actual physical hardware rather than on paper, that the entire strategy of quantum error correction works the way decades of mathematics predicted it would. This is the least speculative, most rock-solid achievement in the entire Willow story. No interpretation debates, no philosophy. Just a hard, peer-reviewed result showing that quantum computing might genuinely be able to scale towards something useful rather than staying stuck forever as an impressive but limited demonstration. And here's what almost nobody's coverage told you. The story didn't stop with that December 2024 announcement. That's where a lot of casual reporting simply lost interest. But the actual research kept sprinting forward. Through 2025, Google kept building on the same underlying architecture, and in October of 2025, the company announced something it framed as a real step up, the first demonstration of what it called verifiable quantum advantage, achieved on Willow hardware using a new algorithm they named quantum echoes. Why does the word verifiable matter so much? Because it clears a meaningfully higher bar. A raw speed benchmark like random circuit sampling is one thing, but a result that outside parties can independently check and confirm, proof that the machine actually did what it claimed, is a much stronger kind of evidence. Google reported this run was on the order of 13,000 times faster than the best classical approach for that task, and crucially, it was designed to be checkable rather than just fast. Around the same stretch, Google widened access to the Willow platform, opening it to outside research partners through an early access program and extending it to researchers abroad, so more of the scientific community could actually run experiments on the hardware instead of just reading about it secondhand. The company also started hedging its bets on the physics itself. In March of 2026, Google announced it was adding an entirely different kind of quantum hardware built on neutral atoms, alongside its existing approach that uses superconducting circuits chilled to near absolute zero. That move matters because nobody in the field is certain yet which physical platform will ultimately scale best toward a truly large, fault-tolerant machine. Google has laid out a roadmap with 6 milestones toward that end goal, and here's a humbling bit of perspective. Willow, for all its fanfare, represents only the second milestone on that road. Just the second. The next steps involve demonstrating a logical qubit that can reliably hold its state over much longer stretches of time, and then a working logical operation running between 2 separate logical qubits. Both are essential building blocks on the path to a genuinely fault-tolerant machine capable of the kind of long, complex calculations that would actually transform drug discovery or materials science. As of the middle of 2026, Google has not yet published peer-reviewed proof of either of those next milestones, and notably, it has been careful not to promise a firm date. And Google is far from alone at the top of this race anymore. IBM has been pushing hard with its own processors, including a 120-qubit chip called Nighthawk, aimed at reaching practical quantum advantage on real-world problems by the end of 2026. Meanwhile, national research programs across China, Canada, Germany, and Japan keep pouring money into their own quantum efforts, each betting on a slightly different way of building qubits, from trapped ions to systems built entirely out of particles of light. Private investment has surged right alongside them, with venture funding climbing sharply as investors who once treated quantum as a distant fantasy started treating it as a near-term race worth real money. So far, none of these rivals have matched Willow's specific below-threshold error correction result on published, peer-reviewed hardware, but the race has clearly accelerated, not settled. And one more thing worth flagging, most security researchers tracking this field still place the moment quantum machines could threaten today's standard encryption, sometimes nicknamed Q-Day, out toward the early 2030s, not tomorrow. Willow and its rivals are real, measurable progress. They are not the overnight arrival of world-altering machines, and keeping those two things separate is the whole game. So let's finally close the loop I opened at the very start. That number, that seemed to break the question of where computation even happens. Here's the honest resolution. You do not have to believe in the multiverse to be unsettled by Willow, and that's what makes it so compelling. A classical computer is fundamentally a machine of certainty, defined input, defined steps, defined output every single time, traceable by hand if you had enough paper and enough patience. A quantum computer is built on the opposite foundation, on genuine uncertainty at the deepest level physics currently understands. And instead of fighting that uncertainty the way engineers normally battle noise, it deliberately harnesses it as the very fuel that makes the machine work. We've been in this position before. People used fire for warmth and cooking for thousands of years before anyone understood the chemistry of combustion. We wired cities with electricity before we had a complete picture of what electrons were doing inside the wires. Again and again, humanity has learned to use a force well before it fully understood it, and the textbooks caught up later. Quantum computing may be walking that same path once more, except this time the force being harnessed is something as strange as superposition and interference. Properties of reality that a handful of serious physicists believe might only fully make sense if our universe isn't the only one. Willow does not prove the multiverse is real, and it would be flatly dishonest to claim otherwise, no matter how good it sounds in a headline. What it does do is take a question that spent decades trapped inside theoretical papers almost nobody reads, and force it into a concrete public conversation attached to a working device you could hold in your hand. Every time we've built a better instrument, the telescope, the microscope, the particle accelerator, reality turned out to be stranger and larger than we'd assumed. So the next time someone tells you quantum computing is just about building faster chips, remember what actually sits underneath a machine like Willow, an operation that seems to strain against the limits of a single universe built by a team whose own lead scientist has argued in writing that the best explanation may reach beyond our reality entirely. That claim is still contested, still unproven, still very much up for grabs. But one thing is already certain. The line between cutting-edge engineering and the deepest unanswered questions in all of physics has never been thinner than it is right now, sitting quietly inside a chip that fits in the palm of your hand. And the most interesting chapter hasn't been written yet.